Hi, this is lesson 8 of topic 4. We're going to discuss intensity of waves and what it depends on, and we'll also discuss diffraction. So let's define intensity first. Intensity is defined as power per unit area. So it's obviously calculated power divided by the unit area. It's a measure of how much energy is incident on unit area in unit time. So the SI unit would be watt per meter squared. Intensity depends on the amplitude of a wave. Now, in simple harmonic motion, high-level students discussed the energy, total energy, depends on the square of amplitude using this formula. In topic 2, standard level and high-level students discussed that the potential energy stored in a spring depends on the displacement from the equilibrium position. So looking at this, the maximum displacement would determine the maximum potential energy, which would be the total energy. And the energy is proportional to the square of the amplitude. So as I said, intensity is proportional to the square of the amplitude of a wave. This is given in topic 4 formulas as such. I stands for intensity and A stands for amplitude. For example, if the amplitude of a wave doubles, the intensity of a wave at a certain distance would be 4 times bigger. Intensity versus the distance. The full version actually of the section of topic 4 formulas, right under the intensity amplitude relationship, we're also given intensity is proportional to the inverse square of the distance. That can be explained by this image. You should remember the inverse square law from your discussion of gravitational field, electric field, etc. So we've heard of inverse square law before, and it means for intensity of a wave, let's take this light bulb which emits a certain power. That would be a measure of how much energy it's generating per unit second. Now, at 1 unit of distance away, let's say 1 meter away from the bulb, the intensity per meter squared would be 1 unit. Compared to that, if you look twice distance away at x equals 2, the intensity, which is power per unit area, would be a quarter of what it was at 1 unit away. Now, this is because the power of the bulb is how much energy it generates per second. That power is incident on 1 square meter at 1 distance away, let's say. At twice distance away, the area the same power is incident on would become 4 times bigger as seen in this diagram. So the intensity, which is the power per unit area, would be a quarter because the same power is incident on 4 times the area of what it was at 1 unit away. At 3 units away, the intensity would be 1/9 of what it was at 1 unit away. So this is to explain that relationship. You might need this in multiple choice questions or comment questions in a paper 2 style question. So next we talk about diffraction. Diffraction is defined as spreading of waves around an obstacle or through a gap. Let's watch this. In my ripple tank, I placed an obstacle. This is actually a rectangular glass bar, and I've used it as a wall to block the path of plane waves that are approaching towards the right. Let's watch what happens. In slow motion, please look what happens in this region right here. You should see that the waves are spreading around the obstacle. Let's see what happens when there is a gap. So now I'm using 2 glass blocks and waves are reflecting from each and passing through the middle, Please observe what happens as they pass after the gap. Now I'm making the gap smaller, and in slow motion, observe the change that you see as a result of the smaller gap. Now, I'm going to use this simulation to explain. This is the simulation I used in my previous lessons. That's the link you can use to access if you wish to try it yourself. Uh, First, select plane wave from the options on the drop-down menu on the right and add a wall from that tab. Make it longer and send plane waves from above to see a diffraction pattern. Okay, what is happening? Now the plane waves are approaching, the wavefronts are straight, and they move at a certain speed. The wavefronts that reach the boundary will obviously reflect. The wavefronts that come across no boundary would move on as usual. But why do they bend around the corner? You can see that after this point, the wavefronts become circular. Their wavelength stays the same, so the separation of these circular wavefronts stays the same as the separation of the plane wavefronts. But instead of traveling in straight lines, the wavefronts become circular. So the wave continues to move in the same direction in this region, but after this point, the spread becomes radially outward. Now, a question I'm going to ask is, if I hide behind a door and keep talking to you, you would be able to hear me, but you couldn't see me. Why? I'm now creating a gap by adding another wall and reduced wavelength. So now you see diffraction through a gap. What we saw in the previous screen was one side of this. Well, now it's happening on both sides. So reflection from here, no change through the middle, but they become circular waves on passing through the gap. So you can see that it becomes a wide circle. Now I'm making the gap smaller, and we'll look at the effect on that interference pattern. And an even smaller gap. Can you see that the smaller the gap gets, the more obvious the diffraction, the more obviously the wave is spreading, because the gap is where the wave continues unchanged, but it becomes circular on the edges, and the more smaller the gap gets, the more fully circular the wave continues to spread. Now let's see diffraction around an obstacle. What we saw earlier was a gap, so I had two walls and a gap for waves to move through. Now this is the opposite. The wave will be able to move on the edges, but there's an obstacle in the middle, so let's see what happens. Smaller obstacle. And an even smaller obstacle. Can you see an interference pattern is formed every time? Feel free to go back and watch every one of these examples. Even better if you go to the website and try these yourself and make observations as much as you want. So let's explain. Now, Huygens principle is what we use to explain this phenomenon. These white lines represent the wavefronts. You see that the distance between them is the same. But we're going to model this plane wavefront as a collection of infinite number of point sources, which emit circular wavefronts of their own. So each of these dots shown on this diagram, you can see, for example, for this one, that would be one wavefront, and that would be the next wavefront. If you look closely, you'll see that the circular wavefronts emitted from each one of these points that form the plane wavefront is represented. But what happens when they emit these wavefronts together, those wavefronts combine to form a plane wavefront, like right here. However, this point has no neighboring point anymore because of the gap. So what happens is the circular wavefront that this emits continues without being able to combine with a neighboring wavefront of a neighboring point. So that's why we see at the edges a circular formation. It was always a circular wavefront formation, just combined forms of wavefronts looking as if they were plane. But when you model a plane wavefront as an infinite number of point sources that emit the same wavelength, we can explain why a wave diffracts around boundaries like this. So what you would see in this example would be a circular wavefront here, spreading radially outward, plane wavefronts in this region continuing straight, and again radially spreading on the other side. This is a drawing I made to help you see another version of this principle. So if you look, these wavefronts are formed by combined circular wavefronts. So this wave is moving forward. When the wavefront reaches here, these points continue to move forward, emitting circular wavefronts and combining as another wavefront over here. But you see, as of this point, on the left of that point, there are no more point sources to emit wavefronts on the next step. So it looks like only circular wavefronts left on this side, so it spreads circular. When it reaches a gap like this, that happens on both sides. Again, this is the same image that we just saw actually. So from the middle, the wavefronts continue to be plain straight wavefronts and circular wavefronts on the edges. And this is why, as this gap gets smaller, this region, where it continues to go straight, gets smaller and smaller, which means the whole shape will get more and more like one circular wavefront. So when the gap is smaller, diffraction is more observable. And it's also important to add that when the gap is too big compared to the wavelength, the diffraction effects cannot be really observed. And this answers the question why you wouldn't see me, but you would hear me if I was hiding behind a wall, because sound wavelength is large enough to be compared to the size of the gap of the door, but light wavelength is extremely small compared to the size of the door, which is why we wouldn't be observing the diffraction effects around a door, and that explains why you wouldn't see me, but you would hear me. Basically because the sound diffracts enough to spread around the door and reach you to allow you to hear me, but light cannot do that because its wavelength is way too small compared to the size of the door. Here I put some images from the simulation to help you try a couple of cases. And here are some more examples of obstacles. And that's it for this lesson. Your homework to have a general review of concepts discussed so far. There were some multiple choice questions that we didn't do starting on page 173. Please complete those ones. And there are 2 questions on page 192 and 193 of your workbook. My next video will include solutions of all these questions. Thank you.